Hello, AP Stats. This is Mr. Kim once again. This will be the chapter one review video. This chapter particularly, I did rush through a lot of the topics and you might be lost in certain questions. I hope this video helps you just studying for the test, as well as understanding the materials covered in chapter one. They're very self-explanatory and very straightforward. So um, I hope that you don't have too much trouble going over these questions here. All right, so without any further ado, let's go over the very first one. It says, which of the following is not a quantitative variable, this says. So a quantitative variable is anything that you can measure from, like, it's a number based. So if you take a look, you can see like the number is kind of occurring a lot for these questions. So a number of dogs in a house means that you can physically count which type of dogs breed, let's say like terrier, there's going to be like 3 of them. German Shepherd, there could be 5 of them. Like you could actually count the number of dogs. Or actually, it's in a house, so house number 1, house number 2. You can physically count how many of those are. Now, a TV channel number is like there's only one distinct channel number for a specific channel. So like channel 141 shows you one network, channel 142 shows you one network. But like you can't really physically count how many channel 141s there are because they all share the same channels. Like it's just one. So B is actually one of the worst to answer here if in terms of quantitative. Quantitative means it's a number-based data that you can physically count. A student shoe size, let's say you have 100 students and then like a shoe size is like 9, 10, 11. You can actually physically represent it with dot plots. Like shoe size 9, there's like 5 of them. Shoe size 10, there's like 15 of them, and so on and so on and so on. So that's definitely a quantitative variable in which we're not going to count. Number of songs played on a radio station in 1 hour. So now depending on one radio station, you can physically count the number of songs. Number of songs stored in a person's iPod. I mean, this is even the better version of answer choice D. So the correct answer here is B, because a TV channel number is not quantitative. It's not something that you can physically count. It's like you go from channel 1 through 100. There's one dot per channel. Like there's only one channel per or one network per channel. So there's absolutely no point in trying to count these because every single one of them is just going to give you one channels each. So that's why for X choice B, it's not going to be a quantitative variable, or it will be the worst one out of the 5 when you had to choose amongst these 5 choices here. Which of the variable is most likely, keyword on the most likely, skewed to the right. Now, skewed to the right means that vast majority of the data would fall on the low end of the spectrum, and only few would fall in the right spectrum. So if you take a look at this, a student's grade on the easy statistics test means that vast majority of the people will do well. So this will be an example of a skewed left distribution where vast majority of them will get a very high scores and only few will do bad. So most of the data will be skewed on the right hand side, making this data to be skewed to the left. So A is definitely not it. Heights of male high school students. Now, heights of male high school students could be more so than like a roughly symmetrical. There's few that's on the low spectrum, few on the high spectrum, but vast majority of the male heights should fall under the average. So that's roughly symmetrical. Number of goals scored in a soccer game. Now, if you ever played soccer before, it's very hard to score just a couple of goals per game. So a lot of goals will be scored around, let's say 1, 2, 3 goals per game. Let's say there's a game where you just dominate and just score like, I don't know, 9 or 10 games. This is definitely going to be a skewed right distribution because there's only few data on the right. There's a lot of data on the left. Ages of male high school students. I feel like males of like high school students from 15, 16, 17, 18. This is what we're going to call like uniformal because every single data, like freshmen, sophomore, juniors, and seniors, assuming we have equal number of them, we're not going to have huge distribution on one side or the other. So D is definitely not it. Color, okay, that's not even quantitative data, so that's categorical. So we can't even measure that using any sort of histograms or dot plots or stem plots. So definitely the answer here is going to be C. Which one's going to be most likely to be skewed to the right. Okay, so now we have a bunch of distributions for histograms. Now let's take a look. This is skewed to the left. That's skewed to the right. I'm sorry, that's skewed to the right. That's skewed to the left. That's obviously roughly symmetrical. This is very spread out, but I will still call this roughly symmetrical in a way. And this would be a sort of example of a bimodal shape right here. Which of the variables are skewed left? Obviously, I told you before it's time. This one. And mound-shaped means like this. It's just an old-fashioned way of saying symmetrical here. So that's going to be x3. Which of the variable has a skewed right distribution? Okay, well, that's obviously the first one. We've already talked about that. Wherever the tail is, that's where the skewed direction should be. Which of the following are false statements about stem and leaf plots? So stem and leaf plots, as you know, goes like this. And then you can kind of, put all the data in there. Now, the problem with this stem plot is the same as the dot plot, is that it is very ideal for graphs that only may have about 20 dots, 30 dots. But let's say you have like 300 data points. You can't really just sit there and list them all out on the dot plot or on the stem plot. If you have a lot of data set, it's very ideal for us to use histograms because histograms are just one straight up bar and you don't have to physically count every single one of the dots in there. So when they say they're used for both small and large data set, that is actually false. So 2 has to be part of it. It's only really useful for just small data sets. Large data set, you want to use a histogram because it's easier to just plot it. For a large data set, you're not going to list out all of the numbers here, like hundreds of them. It's very unethical for you to do that. So anything without a 2, because we're looking for false statements, I'm going to eliminate. So C, B, and A are out. So we're really between D and E. They can be used to display both categorical and quantitative. Okay, so first of all, categorical can never be represented with those 4 plots I shared with you. The stem plot, the dot plot, the box plot, as well as the histograms. They're all useful for doing quantitative, never a categorical. A categorical can be useful for doing, like, let's say, for example, like a bar graph or like a pie chart. Those would be much more of a categorical. The rest will all be quantitative. So one is not going to be false. One can easily see the shape. Yes, the shape can be told from the stem plots. So what 3 is actually true. So the answer here should be D for this one because we're looking for the false statements. All right, so consider the bar chart. So how do I know this is a bar chart, not a histogram? Look at the y-axis. It gives you the average tuition per year. Now, this is not frequency. So as long as it's not a frequency on the y scale, I know it's a bar graph instead. Okay, so the graph is a segmented bar chart. Now, if you have no idea what a segmented bar chart means, it means one data set at 2005, and you can like represent one average tuition based on private, public, or independent, like different types of colleges maybe. So like on one data, they will have a different colored shape. Let's say here, here, here. So this would be for private, public, or something else, some other kinds of universities, I would say. That will be called a segmented bar graph. Or you can kind of represent at 2005, here, 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 separating the 1 year into 3 different categories. So all in all, segmented bar chart needs to have some sort of categories per year, depending on the type of colleges, urban, rural, or private, public, whatever they want to study. It seems like it's just a straight up 1 bars for these guys though, no different colors, no legends shown. So it is not going to be a segmented bar chart whatsoever. The tuition increased less from 2016 to 2007 than 2008 to 2009. Yes, I mean, you can see the sheer difference from 2006 to 2007 that was very small versus 2008 to 2009, it increased dramatically, probably after the recession, right? So what we want to do is number 2 is absolutely going to be true here. So I'm going to eliminate this one. Everything else has 2. If the vertical axis started at 13,000, that would result in a misleading picture. Now, what does that mean? It means that if I were to take a look at this bar graph and now cut it at 13,000, so now it looks more like this. And then let's say I were to kind of like draw this out. Okay, so you really want to compare this to this. Okay, so for question like number 7 for part number 3, when you cut it off at like 13,000, the reason why we want to call it a misleading picture is because the physical shape of the bar graphs has changed. Now, you take a look at this bar, which is more extended than this one. Technically speaking, the data did not change. Like the data is still there, but because of the fact that the shape has changed dramatically, like when you take a look at this, it might be a little bit more mound shaped, a little bit more um, less obvious that it's going to be skewed to the left distribution. Now, when you take a look at this is obviously so skewed to the left distribution that it's painfully obvious. You see, the difference here from this to this, it's only about, let's say, from 14 to 15, which is 10K. Now, when we have all the bars like much higher than, the rest, the difference doesn't seem like that much. Like, for example, if I were to give you something like this, okay, where everyone has a little bit of height, then this doesn't really stand out as often because the rest of them are still pretty very high. But let's say I cut off at here, then it looks more like this. The shape has changed so that the one that actually is the highest value in terms of the, in bar graphs, like it just stands out more. So when the question is saying like if the vertical axis started at 13,000, it would result in a misleading picture. The only reason why it might lead to a misleading picture is because the bar graphs looks different so that the person could make some different conclusions about the shape. That is the only possible explanation as to why I would say Roman numeral 3 would be correct. It's not 100% though for me, but the answer is indeed C. When you cut off at certain y-axis, because you are not showing the full picture of the bars, like even this one itself, this one didn't start at 0 because it doesn't show you the full picture and show you how great of a magnitude it is. Like for example, this one, like if everything was like from 0 all the way up here, this $10,000 of difference, like from here to there, that will not be as big because all the bars are so high. Like I'm not sure how else to explain it other than the fact that when you change your y-axis to cut at a certain location, the difference seems that much of a greater sense because all the bars are the height has been changed. Like the example that I showed you up here. I think this is really honestly the best way I can explain it to you at this moment. So C will be the correct answer for number 7. And let's move on to the next one. Given a stem plot, which of the following is true? Okay, so it seems like this one is an obvious example of what we call like a bimodal shape. I would totally agree with you if you said that. A lot of the datas are kind of clustered on the side. The mean would be a good description for the center of the distribution. So for the test tomorrow, I told you that mean and the standard deviation will not be part of the exam, but it will still be good to go over them, so I'll still share it with you. The mean is never a good description of the center if it's skewed distribution. You do not want to use the mean because if it's a skewed distribution, the reason why to represent the average salary in the United States, like how much a person makes, we call it a median household income, not the mean household income. It's only because these billionaires and millionaires, which we would call outliers, like for example, if we have these outliers on the end, the average will always get pushed towards that side. Like if I have 0, 0, 0, 0, 0 as your data, and you have 100, 100 in your genesis, what happens is you're supposed to be failing, right? You get 0 on all of your assignments, then 100 comes into play, and then your average suddenly shifts from being a 0 to like, I don't know, like let's say 20-ish or something like that, right? It gets pushed towards wherever the outliers are. So it's the same with the income levels. Like if you have a like very low income household income and then suddenly these billionaires and millionaires are like pushing the average towards that, well, that's not really an accurate measurement of how much these vast majority of the people are making. So if you take the median of these 6 numbers, it's still at 0. That's why the best way to represent center in a skewed distribution, it's going to be a median for any skewed distribution. If it's a roughly symmetrical means that the mean can be the same as the median or aboutish, so both of them will be passed as a good measure of center. But since this is not the case, it's skewed on one direction or the other, we call it bimodal actually. Therefore, it's not going to be a good measure of the center here. The distribution is positively skewed. I don't believe so because it's bimodal. If 60 is passing and most students did not pass, that's all above 60. So I think vast majority of the students will pass. The distribution is mound-shaped. Mound-shaped means this, but we have two mounds, so no. So the answer should be E. The range of the scores, yes, it goes from 51 to 99, so it's about 50-ish, right? So therefore, it's going to be E for this one. Which of the following are true statements about histograms? So for histograms, the vertical axis can either be frequencies or relative frequencies. So frequencies we already know. So what is a relative frequency? A relative frequency means it's the percentage out of the total. So for example, like let's say I have 100 students. Out of those 100 students, 50 play football, 30 play basketball, and then like 20 play I don't know, volleyball, right? So the relative frequency means that it's 50 people out of 100. So 0.5, you would say that's going to be about football. 30 out of 100, which is about 0.3, that's going to be the basketball, and 20%, which is going to be the volleyball. So the relative frequency will always be represented as a decimal value, as a percentage. But at the end of the day, for the vertical axis for about histograms, as long as they account for the counts of each of these, for example, 50, 30, and 20, in which they clearly did in what we call relative frequencies, this will pass, and so 1 is definitely going to be true. I'm going to eliminate C because of that reason. They're used for both small and large data sets. Yes, absolutely, because remember, histogram is the only, besides the dot plot, besides the box plots, histograms is the one that's very useful for describing the shape of many data sets. Like if you have 1,000 data sets, like you want to use histograms, not the dot plots or stem plots, because you don't want to be like, plotting all the dots and so on. So yes, that's definitely true. So that's out and that's out. One can easily see the shape. Absolutely. So 9 should be D. Which of the following are true statements? For a given data set, you can make two histograms that look very different by changing the bin width. Yes, you can, because take a look at something that looks like this, and then something that looks like this. If we just change the shape, you can see how by changing the width, it just spreads out a lot more. So the shape, it looked very different. That's the only thing that they said. It can definitely be possible. I mean, the shape could be told in different ways based on how you change the width for this one. For every bar chart, you can construct a pie chart with the same information. Now, the only problem with the fact that they said bar chart is that they could mean like a segmented bars, which means like for one topic, they could have multiple like bars, right? And they could also have relative frequencies along with it. So for every bar chart, you can construct a pie chart with the same information. Pie chart only directs one information per one piece of pie. So like if I were to do this, this only represents like a small portion of that topic out of the whole thing. Whereas for a bar chart, you can have multiple, like for one given topic. For another one, you can have multiple topics there. So there could be subtle differences between the two. So it's too vague. So 2 should be out. Ever symmetric distribution is unimodal. Nope. The symmetry has nothing to do with the modal shape. It could be bimodal for all I care. They could be symmetrical, right? As long as on the left and the right, I can just kind of fold it in half. A bimodal shape could be split in half too. So the only answer here should be 1. I believe that should be 10 is D for that reason. Yes. All right. So given the following comparative bar chart, like I said, like this, right? This one is the reason why you cannot place this into one singular pie chart. Like you can do one singular pie chart for the cats and one singular pie chart for the dogs, but you can't do both at the same time that represents everything. Because you don't know how many dogs are there, how many cats are there, and the numbers could all be mixed up and be different. All right, so the percentage of women who prefers cats is higher than the corresponding percentage of men. Well, that's certainly true because it seems like we have 55% of the woman who prefers, they prefer cat. About 20% of the male prefers cats. So A is definitely true. The number of male dogs. First of all, let's eliminate that. You have no idea how many male or female students there or people there are. They just tell you how much percentage of those number of people prefer dogs or cats. It could be 100 males versus 300 females or vice versa. who knows how many males or females there are? So the number you can't tell exactly. The high percentage of women prefer a pet other than dogs or cats. I don't think so. I think every female either pick dog or cats. About 30% of the people who prefer cats are male. So let's say for the people who prefer cats, you can just add the 0.2 along with 0.55. So that's 0.75-ish or so. Out of the 0.75, the males are about 0.2. So let's say I bring out my calculator here. Ooh. So let's say I open up a new one. All right, so 0.2 out of 0.75. 0.2 out of 0.75. Okay, so that gives me about 26%. 30% seems kind of rough, like, roughly around the same area, but not as good answer as A. About almost half of the dog lovers are female. More than half, right? I mean, because wait, female actually is less. There are more male dog lovers here. So yes, it's definitely got to be A for 11. All right, given the following pie chart on the type of car, so SUV seems like the most one. Students tend to drive cars made in USA. Never talking about the country in this pie chart. Most teachers, not talking about teachers either. Because we're talking about students in the question. More students in the sample. First of all, we don't know how many students there are, so you can't tell me the number. What we want to say is a higher percentage of those students drive SUVs compared to all the other cars. More students drive Jeep. Again, you do not know what the numbers are. And besides, I don't know how many Jeeps there are for this one. Yeah, more students drive Jeeps than trucks. Anytime when they talk about like the number of like the topics, please just ignore them because you want to always relate the pie charts to a percentage all the time, unless they give you a number for it. Like the only reason why you can't do like, let's say for example, C and E is because how many students are there? It's not provided for you. That's the problem. Okay, so the most appropriate graphs to display data on the distribution of favorite foods. Okay, so this is categorical, which means I shouldn't be using those four of the ones that I've been sharing with you. The frequency plot, the cumulative frequency plot, I know we didn't really go over that, but it's talking about how many times certain things happen, like in terms of quantitative data. A histogram, back-to-back, a scatter plot. These are all going to be a measurement of quantitative data. Only a bar chart and pie chart measures categorical, so please remember that. And so the answer here is going to be A for this one. All right, so each of the box plots shown contains 24 student scores in two different classes. Which answer best describes this place? Class A had more people in second quartile than Class B. So second quartile should be the median. Had more people? Well, they should have equal number of people, which is 12 and 12. I mean, the Class B certainly had a higher median, but it doesn't mean that they have more people. They have the same amount of people, same amount of data in the first 50% of the data. The Class A and Class B both have the same number of people passing the test. Well, what determines passing? Above 60? I don't know where 60 is either. Is that a 60? Is that a 7? Like, I have no information for B. Class A is somewhat asymmetric, while Class B is skewed to the right. Nope, I would say it's more skewed to the left. Okay, so there we go, skewed to the left, and it's noticeable outlier as well, while Class A is somewhat skewed. Okay, well, I would say A is more close to being symmetrical. So D and D kind of talks about shape, but remember what I told you about the box plots? That the shape is never determined 100% from box plots, even though you can kind of say Class A is roughly symmetric, and the College Board will not take off points for that because that you have a reasonable I mean you have enough reason to say that in the first place, so therefore they're not going to take any points off for it. But at the end of the day, please remember box plots, you can never tell shape 100%. Now the correct answer here will be E. The lower 25% of Class B are much more spread out than the lower 25% of Class A, making Class B skewed left distribution, which we should totally agree with. See, the lower 25% is here, and the lower 25% for Class B is actually from the outlier. That's from the outlier, or even if you consider from the next highest number to the first quartile, that's the first 25%, and you can see how much more of a wide spread that is compared to class A right there. So E is definitely the right answer. All right, so 15, a teacher found that the mean number of hours, again, mean is not part of it, your exam tomorrow, but you should be able to do a question like this. If I have 12 students and the average was 6.7, that means that the total divided by 12 is equal to 6.7, because that's how you find the average. You add them all up, divide by how many there are, and that's your average here. So 6.7 times 12 is what I'm going to do. What is it? You know what? I don't feel like really doing that in my head. So 6.7 times 12, so that's 80.4. And then a new student reported 11, so I'm going to add 11 to that. So my new total is 91.4. Now, what is my new mean? Divided by 13 now, because we have 12 students, adding one more will give me 13. So the correct answer here should be B. 7.03 is closest to being 7.0. Let's start from question number 16. A small department at university is seeking faculty raises. The university claims that pay for faculty in the department is comparable to the other departments on campus. So the university is saying they're about the same, but the department claims that they're paid far less. The university and the department both based their statements on the measure of typical salary using data that included salary information for all faculty administrators at the university. So what makes the average salary to be about the same? Even if there were huge outliers, how would they be comparable? Well, you're talking about resistance here. A resistance is, even if I were to put a strong data in, if the properties and the numbers do not change, we call it resistant. For example, median is a resistant property, because if I were to give you 1, 2, 3, 4, 5, 6 as my set of data points, my median is 3.5 currently. But if I were to add a number at the higher end, say 100, which is a far extreme outlier compared to the rest, the average will be ridiculously high. Like, it will change from 3.5 to something that's way bigger than that. But a median, because you're crossing out the 100 with 1 on an equal portion, you keep on crossing out the middle, and now your median is only up to about 4. So it did change, but it changed so slightly a bit that we call it resistant to these extreme changes that could be brought upon. So if the university claims that the pay for faculty is comparable to the other departments, that's only because they use the median, a property that's resistant to these high boundary levels, high boundary values. So that is the one thing you're looking for. See, now the department claims they are paid far less because they're using average. See, the average value for the other departments, they might have some people that's making more, pushing their overall average to be on the higher end. So that's why they're saying, we're actually earning far less. So the university compared the median salary, whereas the department used the means. First of all, anything that's talking about the mode, like I saw these two, please eliminate them, because they're the garbage answers right there. The university compared the mean salary and the mean. So if they actually use the mean salary for the university and then department use the median, opposite thing should happen. They use the mean salary and then department also used means, but then they somehow made a mistake. No, they should come up with the same conclusion. Like, they're about earning in the same manner, and they should come into the same conclusions. But the only reason why they're having some feud over here is because there's some difference in the numbers that they got. And so the correct answer here should be B. The department used the means, the university used median. And lo and behold, on 17, we have a question regarding the resistance. Anything that's resistant are the following. Median is resistant, IQR resistant because adding one more data set will not really change your Q1 and Q3 that much. The one that's not resistant is pretty much the opposite. So the mean is always not resistant to change. Once you look at your Genesis grade, if you've been failing all of your things and then you suddenly get like massive 100, your grade is bound to go up. Like, your average will change dramatically. Same thing for standard deviation. I told you that we're not going to talk about these two, but standard deviation is a measurement of spread from the mean. So these two are the most most non-resistant values or properties any distribution could have. So let's eliminate anything that says the median for B and D. I also see interquartile range for A and C. So the correct answer is E, mean, variance, and standard deviation. Variance and standard deviations are pretty much saying the same thing. We'll go over that later. But when we're talking about the resistance of the data set, it should be E. Anything with mean, standard deviation, they're the least resistant. Median and IQR, they're the most resistant. A group of 24 AP students measured the length of time it took for chocolate to melt. So those are my 5 values, approximately how many chips had melted between 12 to 29. If these are 80 chips, remember, that's 25% of data, 25%, 25%, 25%. How do I know it's 25? Well, from here to here, that represents the 100% of the data. Min to Q1 to median to Q3 and maximum, I told you before that they actually divide the data set up into 4 equal pieces. So from 12 to 29, the number of data sets within those 2 boundaries is 25% of the entire data. Like if there were 100 data sets in here, that means there's going to be 25. If there's going to be 1,000, there's going to be 250 data points basically. So if there were 80, that's splitting up into 4, so that should be 20, 80 divided by 4. Number 19, using the following box plots to answer 19 to 20. Now, when I did this, 20 was pretty obvious because we kind of have one obvious outlier here, so I know that that's for E. Now, for this one, you might not be so obvious, but first let's eliminate D and E for this one because we don't have any outliers, it seems like. We can kind of see that it's roughly symmetrical. You might argue that it's maybe skewed a little bit to the left. However, in all, they are going to be pretty much balanced out throughout the whole thing. And also, if you notice, vast majority of the histogram bar itself, they're kind of around the same level, and which means they're most likely to be really well spread out. So what that means for me is I have to eliminate B because this means a lot of data is congested around that area. Like if I were to represent a dot plot, so many dots are plunged around that the spread, the variability from the 50th percent to the 75th percent, the quarter of that entire data set are all congested into this one data with wherever that may be. But you can see how this is much more well spread out. So you're looking for a well spread out distribution graph between A and C. C is a much better choice because you can see how well evenly that's all spread out throughout the whole thing. Whereas A, it's more like there's a little bit of difference here, a little bit of difference there. And truth be told, the spread is just way too short from the minimum to maximum as well. So the correct answer here should be C. The box plots below summarizes the 2 data sets. Which of the following set must be true? Set B has a higher median. Okay, well, that's definitely true because we know that that's the median. Set B has higher. Set B contains more data. Nope, because we do not know how many data sets there are. They didn't say this one has 100, this one has 120. You never know that. So everything with 2, I'm going to eliminate. The data in set B have a larger range. That is so not true because it's set A that has the larger range. So I believe 21, yep, should be A. 22, according to two-way table, what percentage of males had their first crush before the age of 13? So this is a the conditional probability given that it's a male. I believe that's 45, 13, so that's 58. Out of 58, how many had crush before age 13? That's 13. 13 out of 58, that should give you about 22% or so. So that should be C for this one. All right, so now it's the free response questions. With the table below displays the data on several roller coasters that were opened in 2009. So what individuals? It's D. So the roller coasters are the individuals that we're trying to study. Identify each variables which are quantitative, anything with the numbers in it, right? So the height is a quantitative, the speed is quantitative, and the duration. They're all quantitative variables. The categorical is how you would describe it without using numbers. They're sitting down, flying, the designs of the roller coasters, and such as the type. Because I don't feel like writing these down, I'm just going to draw lines, and you guys can figure this out. Next, number 24. In few sentences, describe the similarities and differences. Okay, so again, on the day of the test, you're going to write down complete sentences, but let's just talk about what are some very, very subtle differences between the two. First, the spread. Obviously, for after, the spread is larger. Specify the number between maybe about 3-ish to 63-ish, whereas the before is about 3-ish to, I don't know, about 45-ish or so, I would say, 45-ish or so. So we want to say that for after, it's definitely higher. Another thing, max is higher for the after. And again, median is also higher for after. Now, you're not going to do this on free response. I'm just going to give you some bullet points that you will need to address. Please put them in complete sentences. So we talked about center, the median, the spread also. There's no apparent outliers for both, which could be our similarities. So apparent outliers for both. And what you can say is they're both going to be roughly symmetrical for both, / even though box plots can never tell shape. Like I said, you can make a conjecture as to how this is going to look like by looking at the minimum, middle, and the maximum. Median, the minimum, middle, and maximum. Like if you were to kind of see how much of a spread the 50-50 percentage of the data sets are there, you might just say that this is roughly symmetrical because of that reason. Like it's well spread out, and then there's one, median, could be possibly be peak, or what else? How do you, you never know. So the shape, if you said roughly symmetrical for both, I will accept that. You have a reasonable evidence to be able to prove why your claim is going to be true. And I believe that's pretty much it here. You can talk about the IQR rule too, IQR too. IQR is smaller here than IQR on the after, but it's the same thing as talking about the spread anyway, so there's no point. Did doubling the dollar value of the question tend to result in greater amounts won? Yes, obviously. Provide justification. Well, you really want to take a look at the median, right? Well, the median here for before, it's around maybe 21-ish. And for after, it's about 30-ish. And remember, winning players prize in thousands of dollars. After they actually double the doubling the dollar value, there's going to be players prize money. Is the 30 actually represents what? To the below compare box with winning contested prize money before and after the change in the dollar values. So the motivation is definitely higher because the price, the doubling the dollar value. So we actually increase the value of the money. So we have greater amounts won simply because of that reason. Provide justification could be because people are greedy and they want more money. And so the maximum has increased, the median has increased. They're much more, the second half of 50%, they earn just a lot more money. And so there's going to be huge variability there, huge amount of numbers. And so far, yeah. So that is what you would say for proving the justification. Because the dollar value has doubled, people might be more motivated due to greed. And then okay, so Jeopardy produces double the dollar value. Yeah. Of the winning contested prize money before and after. Yeah, so because they double the value, they're more greedy and they're much more motivated to play the game and get those questions right. Therefore, there are greater amounts won for those questions. Simple human behavior, right? More money given, they're going to be more driven to play, more driven to win. All right, number 25, below are travel times in minutes, 15 workers. Now, I have no choice but to put these in my list here. So I'm going to go to my calculator and go to stat, and I'm going to type all of these in. So I'm going to do 30, 20, 20, 10, 40, 20, 40, shoot. 25, 20, 10, 60, 15, 40, 5, 30, 12, and 10. And another 10. Good. So there's 14, or there should be 15 number data sets. So I think I'm missing one. Yeah. So that should be 40, 5, 30, 12, 10, and 10. So there's 15 data set. So go to median, calc, one var stats. There's no frequency list. So my mean and median would be 22.46, and then my median would be 20 respectively. The range would be from minimum to maximum, which is 55. The IQR is 20, since we know that the Q3, it says it's 20, Q1 is 10. Now, compute the limits for outliers. So IQR is 10 times 1.5 is 15. So the limits for outliers should anywhere between -5 to 35. So anything above a 35 would be considered an outlier, which means it's 40 and the 60. There should be 3 outliers here. Compute the standard deviation. We know that that's going to be the one that we have up here. Okay, so for number 25, yeah. So if you just take a look, SX, I know that the sigma x is 14.47, but the sample standard deviation, that will be the standard deviation for this. So we have 15.23 as our standard deviation. Name the 5 number summary as I showed you before. 5, 10, 20, 30, and 60. These would be my min to maximum and the interquartiles and the medians and things like that. Okay, next, draw a histogram that will be classified as skewed to the right. So skewed to the right means we have a lot of data set here, but only a couple data set there. Skewed to the left will be the complete opposite. So you can have like data here, but just kind of just a little bit few, I guess. So the tail is on the left, tail is on the right. Symmetric means that every single data set is pretty much the same bar. So you can kind of draw like a one straight line, and that's called that's called uniform. And symmetric means obviously roughly symmetrical. We can just do something like this. Okay, so now the 2 AP teachers within a school district, blah, blah, blah. Teacher A, teacher B. Draw comparative box plots. Oh, box plots, okay. Which means I have no choice but to put these into our list. I'm going to use my new list here. So I'm going to type in 59, 86, 92, 42, 71, 73, 78, 80, 75, 84, 73, and 78. So that's 12 data sets here. Did I tell you? That should be 12 data sets. Yep, that should be 12 data sets. All right, next one, 67, 68, 70, 55, 60, 95, 86, 72, 85, 80, 74, and 59. All right, so I have those two, teacher A and teacher B in those two lists. Now let's see if I can do the box plots here. Stat, calc, one variable stats for list 2 this time. All right, so here, though, that's my 5 number summary for this. So that's 42, 72, 76.5, 82, and 92. Now for this other one, I'm going to change this to list 3. And what I get is 55, 63.5, 71, 82.5, and 95. All right, so I have those 5 numbers. Remember, if I want to draw a comparative box plot, you must make this on the same scale. My numbers range from 40 to 90, so I'm going to make from 40 to, let's say, 100, 50, 60, 70, 80, 90. And so I will do the best way that I can to estimate this. 42, 72, 76, 82, and then 92. So that's my box plot for teacher A. And for my teacher B, it will be from 55, 63, 71, 82, and 95. So that will be my box plot. Okay, now you can clearly see that the spread is definitely different for teacher A and teacher B. Were outliers detected? Explain how you arrive at this answer. Okay, so the best way to do this one is for B, I don't really think there is going to be an outlier, but just to check, let's say I do the fourth one here and I do list 2. Zoom 9. Okay, so there's definitely one outlier for, as you guys can see here. Ooh. I want to zoom into this, but I really can't show you on the zoom in for the calculator. A has an lower boundary outlier, I believe, at 42. And the next highest number is, I think, it's 59. So at 59, that's where they cut off the tail. So I'm going to erase the bars in the whisker in between. And so that will be my teacher A. Let's do the stat plot with list 3 and see if we're missing anything. Actually, that should be list 3, and then we're going to clear this. Okay, there we go. So we don't really have an outlier for part the teacher B section. So we're all good with that. So what were outliers detected? Yes, for teacher A. Explain how you arrive at your answer. You guys know the deal. It's 1.5 times IQR. So the IQR for teacher A is 10. But now you multiply that by 1.5, it's 15. When you subtract 15 from 72, you should get, what would that be? 57. And add 15 on top of 82, you get 97. So 42 is less than 57. Which means that's why 42 is labeled as an outlier. The next highest one is just 59. Well, 59 is bigger than 57, so it actually made it. It's not lower than 57, which means it's going to be considered as an outlier. That's the cutoff line. So that's how you can say you've arrived the answer by using the 1.5 times IQR rule. Who appears to have gotten better results from their students? Justify your response. Now, if you take a look at these two, the teacher and teacher B skills are very, very kind of close to one another. Yes, teacher A had reached a higher maximum than teacher B, I'm sorry, has reached a higher maximum than teacher A. Oh, I guess then there is no competition here. So this is definitely a teacher B. I think that's also what they said. Yes. So the reason for that is because you can see how all the numbers are very comparable on the higher end. The max and Q3 are definitely higher, and also no outliers on the low extreme on the lower side. The minimum is higher, which means you can feel safer with teacher B because the lowest possible score that teacher B ever got was a 55, whereas for teacher A, this one student just bombed it and got 42. So in terms of who has gotten better results overall, a higher maximum and a higher minimum and a higher overall quarter 3, even though the median for teacher A, you could kind of support for teacher A using that, but all the evidence just kind of flows for teacher B. It's like teacher B has like 3 advantages, where teacher A, the only advantage it may have is that the median is higher than teacher A. I'm sorry, teacher A has a higher median than teacher B, but that's the only thing. So all of these accounts for the reason as to why teacher B is better, and that's what you would say. All right, so now we're finally down to our last question, Python eggs. We have a 2-way table. What proportion were randomly assigned to hot water? I don't know why the review for chapter 1 has these random chapter 5 questions, but we're still going to do it. Of the eggs hatched, which means this, 129, so conditional probability. Assigned to hot water is 75, so that should be the correct answer there. Part B, of the eggs that were randomly assigned to hot water, so 104, what percent hatched, which is 75. Now, the mosaic plot, they actually have these, what we call width. It's same thing as saying segmented bar graphs, like I said, but the only difference is that the width tells you how much of the frequency, how much of the numbers there are. The mosaic plot displays the distribution of hatching status by water temperature. Describe what this graph reveals about the association. So you can see how I should probably use different color. As the water temperature increases, the relative frequency, the percentage of the number of eggs that hatch that says yes, the green amount keeps on going up. So the association, what you want to do is make a sense of the relationship between the two. As the water temperature increases, the percentage of hatched eggs went from 60 to 70, to maybe about 60, I don't know, 80%, about to 70. Therefore, there is an association between temperature and the percentage of eggs hatched, semicolon. The higher the temperature, the higher the rate of eggs hatched. Something like that. That's what I would probably most likely say for this. That is, I think, what the answer key also says as well, that as the more likely chance of you getting eggs hatched is from the hot waters rather than from the cold waters. And I think that should pretty much summarize every questions from chapter 1 here. Whew. All right, so with that being said, I hope you guys can study well for tomorrow, and if you have any questions, just please let me know. I'll see you guys next time.